present on MBSE journey at Applied Materials. So how we kind of realize the full value of the MBSE models that we developed for our product architectures through digital thread implementation by connecting to downstream data. First, I'll give some introduction and context and why we chose MBSE to solve some of our key problems, and explain a little bit about our MBSE and digital thread production pilot implementation, and what are all the accomplishments, challenges, and learnings, and what's next in our journey in upcoming years. First, who are we, right? So we are world's number one semiconductor and display equipment company. We provide equipment to manufacture chips and display to various customers like Intel, Samsung. So virtually like every chip being produced in this world, one way or other, Applied Materials have involved in the material science, behind that. So we have about close to 20,000 patents in the semiconductor industry, and we have factories and foundries across the world, with presence in 24 countries, and we are headquartered in Bay Area, Silicon Valley at US. So our vision is to build a digital engineering ecosystem where we connect the upstream data, digital artifacts, and also business processes with the downstream. So starting with the systems engineering and the product development of detailed design and manufacturing and service. So we are planning to, or we are already working to connect the digital artifacts, towards our product lifecycle, and we have matured our digital landscape in some of the areas than the other. For example, we have a strong model-based definition, the detailed design. We use enterprise PLM and CAD applications to build our MBD, and we've started our work on the systems engineering side, where we choose Capella or SMW for our MBSE model-based systems engineering. We build the models, and we also started with the requirements, team center requirements, where we build our requirements starting from marketing, functional design, and software. So the idea is to have a single source of truth that integrates and tracks all the data across the entire product lifecycle, and also connects the stakeholders and make sure that the information is available for them, and not just making it accessible, but also make it actionable information for them to work on that data. So this is our vision, but why do we need that, right? So why we need that comprehensive digital thread and digital engineering ecosystem being built? Because we have our compelling business needs. For example, in the semiconductor, we have this PPAC, where we need to improve the power, performance, area, cost, and also time to market. As you all know, the AI revolution is happening in front of us, and chips is the heart of AI development. So we have to make sure the power consumption of all those data centers for which is running the LLM needs to be very low. Otherwise, it's getting out of control. And other thing we are doing is integrated material solutions for advanced scaling. And one other key aspect is sustainability. As you know, all the industries almost are being pushed for that, and I know we are no exception. So there is a growing pressure on our industry to achieve the net zero. Both the fabrication and also the operation of our equipments at the customer sites. How we can bring up the power efficient chips, but also how we can manufacture those chips with less power and less emissions. So because of this compelling business needs, and also with our existing systems that we use for the product development. For example, a lot of our business processes are were document based, like requirements management is document based and it's not integrated with the PLM system. And we do have product architecture built for many of our products, but it's also document based, presentation and other things. So there is no um, um, tools like Capella, where we have developed all those models and can be reused at any later point of time. So given these business needs, plus that kind of creates a complex products, but also the document-based processes that we have. We wanted to uh, build that uh, comprehensive digital engineering ecosystem um, to avoid the silos of or the siloed processes and disconnected artifacts in our company. We started with evaluating some of the MBSE uh, tools and technologies that are available in 2023. Mainly the objectives was to improve the communication between the stakeholders, productivity, reusability of the product architectures, because most of the time we do a lot of changes to different customers, but our basic core product architecture will be same, and apart from building new products, of course. So we have to have ability to reuse some of the models that we develop. So that is also one of the core objective, and also supports integration with various other enterprise applications that are present within our organization, where the data flow can be smooth. Because we can develop all the MBSE models separately in a standalone application, but if not connected with the downstream processes or tools, then it might be difficult for the consumption. So all these things are important objectives. With those objectives in mind, we evaluated Capella or SMW, Systems Modeling Workbench. Just to give a small overview, Systems Modeling Workbench is a wrapper built on top of Capella to enable the integration with Siemens PLM, which is called Teamcenter. So wherever I mention SMW is basically Capella, um, uh, built in a way to integrate with Teamcenter, and also a few other MBSE tools we evaluated like Cameo and Altair OmniV. And for the requirements management, we evaluated Polarian and TC requirements, TCM and Teamcenter requirements management module that is available within Siemens Teamcenter. So some of the core factors that decided, that helped us decide to go with Capella or SMW and Teamcenter recommends are mainly the ecosystem, right? Siemens ecosystem, because it's tightly integrated. So we could create those models in Capella and publish those MBSE models into Teamcenter. And other than systems engineers, any downstream engineers can consume the MBSE models in a very lightweight fashion within the Teamcenter web interface. So that added a huge value for us because we don't have to invest much on the IT infrastructure side on integrating the MBSE with our existing PLM application. And it's also extendable, right? So Capella is something that you can create your own item types or which suits your industry needs. So it is very much extendable compared to other tools. That is also one of the reasons why we picked Capella. And Academy methodology, it's very well suited for our complex products, like explain the business needs and the problems that we are trying to address in our industry. Our products are very complex, so having the ability to split the models with the operational capabilities, system, logical, and physical, creates that clarity. Even though the product is very complex, but in terms of consumption or even in terms of creating the architecture from the systems engineers, Academia methodology really brings that clarity for the for us to build the system models. And in future, it also will have the SysMLv to export compatibility, which we definitely need. In case we are going to develop the system level simulation models or other system level models in SimCenter Studio or other applications. So the SysMLv to export capability comes really handy. And I know we also observed that it's a shorter learning curve in Capella compared to other tools. With the community is very strong. We could have a lot of we have a lot of training materials available in the internet, YouTube within Capella forum. So that helps the shortening the learning curve for the systems engineers. And finally, on the Team Center requirements, it's a really easy to use interface. So it's almost like you're editing the requirements in the Word document, but you could do within the Team Center application. So those are some of the core factors why we chose Capella based MBC solution, and we implemented this production pilot this year. And we are also working on various other proof of concepts, which we talk about in a few minutes. We picked a couple of product architectures like electrostatic check and plasma system, where we build operational capabilities, diagrams and elements, and also system architecture with detailed system functions and also physical architecture. The reason why we specifically skipped logical is because the product architectures that we chose for our initial production pilot is something that we have already developed. So it's kind of a re-engineering, similar to the presentations that we saw earlier today. So we have already established connections and interfaces between those different physical components existing, and even system components that are existing. So we kind of skipped the logical to make that transition to MBSE models a little bit easier for the systems engineers to reduce some workload. And another reason is we are giving more emphasis on the physical architecture because we are trying to connect the physical architecture models with the CAD and other detailed design that are available in our enterprise PLM. So that's the reason we picked only these three um, aspect of our career for our production pilot. But in future, of course, we'll be leveraging the logical architecture capabilities as well. So the main, one of the core reason, of course, not only solving the upstream um, issues that we had with document based recommends management, document based system level models which are not reusable and not integrated. Of course, that's a huge value add from adopting the MBSE. But the one other key important factor is how we can leverage these MBSE models to build a digital thread connecting the downstream data. How we can make this consumption of the MBSE models really useful, say, for example, for the design engineers, for the quality and reliability engineers, even for the simulation, like CAE engineers. So that is our key long-term goal. So we did this proof of concept where connecting all these digital artifacts, starting from the requirements to the system architecture, which is MBSE models, and then to the detailed design, the CAD pods within Teamcenter. That is the BOM, basically connecting to the BOM. Then also connecting the design with the quality and reliability data, for example, the FEMICA, other reliability physical test results, and some of the supply chain information like cost, A for like annual failure rate of the part. If that particular component is being already used in the production, then what is the rejection rate for that part? So based on that, we can make some design decisions while creating this architecture at the MBSE level. So this is the digital thread that we are trying to connect, and in future, of course, we are planning to extend to connect the Z-bomb to M-bomb and bill of process using TZ manufacturing solutions, and also ultimately to connect to the service bomb and issue management. To look into the issues that are coming from our shop floor or even our from our customer sites. So to have the end-to-end traceability from the recommends to design to validation to manufacturing and service. So that's the overall digital engineering ecosystem. This will allow us to create a lot of digital twins. So once we have comprehensive digital thread built in our ecosystem, using those digital artifacts, we can create those digital twins so that we can assess our product design well ahead of the time. Instead of doing the physical test on the prototypes, we could, for example, we can run the simulation, superimpose the simulation data on top of CAD data, and visualize, how our design is actually performing in various conditions. For example, with different recipes, different, external conditions, how our system design is performing. Without even going to lab, you could have those assessments coming from the digital twin. So I'll talk in details like how we built those digital thread using the MBSE models as a source. So for example, we started with the requirement specification. So this is one of our plasma system that we built. So we built all the requirements within the Team Center using requirements management module, where we not just build the recommend structure with the specification and all those things. So we basically did that recommend decomposition process in conjunction with the building the architecture in the Capella. uh, because we typically start with the marketing recommends, right? Whether it comes from the customer or the product team doing the product research. So we start with, let's say, 20 marketing recommends. This is the high level recommends for the product that we need to design a product or make some changes in the existing product. So we start with the operational capabilities. But while we are doing the operational capabilities, we realize some of the recommends are not detailed enough. So we go back to the table and discuss with the product engineers and sometimes systems engineers to uh, describe more details into those requirements. And from that marketing requirements, we derive and create the functional requirements. What are the functions that the system have to perform in order to satisfy those marketing requirements? Similarly, what are the design requirements to satisfy those functional requirements? Because you could have multiple design requirements satisfying a single functional requirement. So likewise, we did this requirements decomposition process in parallel with developing the architectures, like system level architecture as well as physical architectures in the Capella. So it's a multiple iterations. So we learned a lot in the process. So while doing that, we also standardize the recommend specification, recommend structure that is being put into place, and also we trace linked each individual recommend. So for example, if you have um, 5 design recommends, and you could have one or more physical components that satisfies those 5 design requirements. So you trace link or create a relationship with that physical component node to the requirement so that you can see. So if anyone, a design engineer, looks at the MBSE models in the team center, they can, look, for example, a puck, which is a physical component. They can trace back, okay, these are the design requirements that resulted in this creation of this puck physical component, and this is the CAD part, detailed part that is already available in the team center, which might be used for this puck physical component. So that traceability between the requirements, MBSE, and CAD parts was created, and it is very useful in terms of reusability or even in terms of change management. If you want to make some changes um, quickly, then it is very easy for you to um, track down the individual components or subassemblies in the CAD parts um, and make changes. And also Teamcenter has a very easy to use architecture viewer. So either some engineers, they can open up the Capella to see the detailed view, detailed architecture diagrams, but they could also see the simplified architecture within Teamcenter or the relationships tab, or they could simply see the architecture diagrams being exported as a JPEG image datasets within Teamcenter. So the consumption is really made simpler for non-systems engineers. So, and one other aspect is like connecting to other downstream data like quality and reliability data, right? So this is very important because looking at these downstream data in the context of product design decisions, right? So while let's say you are making a design, you are making a recommend change for an existing product. Based on this recommend changes, you have to look at the existing CAD parts that are used for this design and make a decision. Okay, for in order to satisfy these recommend change, can I use the same subassembly with some changes, or same component with some changes, or maybe use a different component because this component is used in the production flow right now with high rejection rate, meaning the annual failure rate is more than 15 percentage. Depending on your company's threshold, you can decide, okay, this failure rate is uh, really high for this kind of product, so we are not going to continue with this supplier or with this component, and then we can switch to a different product. And so that I have to make some adjustments in the MBSE models to reflect that new product design. So you can make those design decisions well ahead of the time, like shifting left, by uh, having this availability of downstream data connected to the MBSE models, which adds a huge value and reducing the time in product development. So likewise, we have added the FEMICA data which explains the failure mode and potential causes of those failures. What are the process controls in place, not just at the assembly levels but also individual components, like annual failure rate data, and also like physical reliability test. Some of the prototype parts we receive and we do the test in the lab. So we do very intense testing depending on the product. So we also have those test results available directly, trace link with the design, which can be used again to make the design decisions, um, while creating the or making changes in the design architecture. And finally, so not just connecting the digital artifacts, the next level is having the data flow. So for that we are leveraging the integrated parameter management. So we are doing a proof of concept, uh, where basically this model will help us sue the digital thread, connecting all the artifacts and also stakeholders in the product development process. So to take for an example, so we have certain requirement targets. So for example, the wafer inner temperature have to be in certain range, between 30 and 80 degree Fahrenheit. So that is the parameter targets for a given requirement. And based on that, we build the MBSE models in the Capella. We let's say we have the cooling plate thickness and material have been designed. So those are the design parameters. So the cooling plate thickness will be like zero point 0.5 mm. The outer diameter, is like 1 mm, etc. So and then materials what we choose. So all those design parameters are configured within the MBSE models. So we kind of blurred, but you could see here, those design parameters are clearly mentioned for individual physical components. Um, so now we also have some of the high level simulation models. I know those models will use these design parameters as an input, and then run the simulation and get the results and validate our output, CA output, against the recommended parameter targets. So that is a proof of concept which we did, which I like explain in the consecutive slide in detail. But the idea is not just connecting the digital artifacts and having the relationship and trace link, which is hugely useful, but also facilitate the data flow between one business process to other, from the requirements to design to validation, smoothly. So for that, the integrated parameter management comes really handy, and Capella supports that. um, very easily. You can just drag and drop the parameter definitions from the Team Center interface directly into the Capella, and I'll add those design parameters uh, towards to the physical component or physical functions. So this is the POC in detail. Like so, of course, the MBSE model that we built in SMW or Capella, and Team Center is where our requirements are being built. And we use Jupyter Notebook as a single interface for this proof of concept. But and also we use py-capella MBSE add-on to extract the information from the MBSE models, and we use Matplotlib for generating graphs, and MATLAB as our to run the simulation model. So in this example, we picked a MATLAB model of electrostatic check. So I'll quickly run through the process that POC has. So first step is to extract the design parameters. Sorry, the extract the requirement parameter targets from Team Center. So like I was explaining, the inner wafer temperature or the layer temperature in the electrostatic check. Those are the recommend targets. Either comes from the marketing recommends or functional recommends, which says that the temperature range has to be within certain um, values that has to be met. So first we extract that information. Then we extracted the design parameters from the MBSE models. Like I explained, there are two types of design parameters that we use. One is material parameters. The other one is geometry related parameters like outer diameter, thickness, etc. So we extracted those design parameters from MBSE models using py-capella MBSE, and we use some other Python libraries to visualize that data in a table format very easily for the systems engineer within Jupyter Notebook. So as a systems engineers, they just open the Jupyter notebook, so everything happens within that interface. That is the idea. So once we extract the design parameters from the MBSE models, so we are going to run the CAE model, which is a MATLAB model in this case, which is basically the high-level electrostatic check. It uses the geometry and material design properties and runs and gives you various temperatures that will be recorded, like the wafer, the cooling plate, and different layers. So, you could use one or multiple layers between the cooling plate and wafer. So those temperatures are recorded, and the MATLAB model will give you those output. So initially, without making any changes, the systems engineer will run the CAE model, and it will give you an output. Now you can validate that output, CAE output, to see whether it satisfies the new recommend targets that is being set. So it will say that, okay, some of the recommend targets are not um, met, um, because of the changes that we made in the requirements. So what the systems engineers can do is they can actually alter the design parameters directly in this interface in the Jupyter notebook. So they could change, again, as some of the in this case, the layer temperature was out of range, so they could change the layer thickness. This type of electrostatic check, we use 4 layers. The layer one thickness, they have altered it, and then the material they altered as well. So based on that, they again they can rerun the CA model with the modified design parameters, and they validated that output against the recommend targets parameters. And this time it satisfies the target parameters. So now we know the new design parameters, which would potentially satisfy those recommend targets. So this um, code will automatically update those design parameters in the MBSE model. So they don't have to go to manually update the design parameters in the Capella. So rather, this interface, again, Jupyter Notebook, they could directly update the um, parameters in the MBSE models in Capella using py-capellambse functions. So end to end, the full cycle can be done within the single interface. And this is the proof of concept that we did, added huge value. But the idea is to build this with various other simulation, like physical simulation using ANSYS or CFDEAs or other simulation applications, not just limited to MATLAB. So we are trying to build this workflow within the Teamcenter using TC Sim module. So ultimately, we will have this. Use this integrated parameter management and TC Sim to build this digital thread connecting MBSE design and simulation within Teamcenter. That is the project we'll be working on in the upcoming months and years. So some of the key outcomes is, like as I described in our production pilot, we picked 2 product architectures: electrostatic check and a plasma system. Overall, we built greater than 50 physical component nodes just to show the complexity or the volume of the models that we built. And it has greater than 200 physical functions, almost about 100 physical links, and a lot of functional exchanges and 50 system functions as well. As I mentioned before, so we had operational capabilities, system architecture diagrams, and then we derived directly physical architecture, skipping the logical, at least for these product architectures. And we also standardize the requirements for these 2 product architectures. So we have about more than 500 requirements, combined for these 2 product architectures. As I said, it's getting decomposed, from the marketing to functional to design, software, all those different types of requirements are being built under the requirement specification structure in Teamcenter. And we also established the traceability between requirements to MBSE models to MBD in the Teamcenter, and we have about 15 CAD assemblies that are trace linked uh, to the MBSE models. One important thing is so that the decision to exactly which BOM item you need to trace link with the MBSE model is really depending on how deep you have to go. So in this case, we picked like subassembly levels. We did not go component levels. For example, the if you have puck as a physical component node that you created in the Capella, you will have the puck assembly in the team center. That the cat sub-assemblies will be, or it is already trace linked there. So instead of going to the individual components of that assembly, but it depends on your use case. We could go to the component level, or we could stop at the sub-assembly level. And overall, this digital thread is really useful because of the information the systems engineers and design engineers will have uh, well before they start the design, so they can make very important design decisions based on the data that is available for them. So some of the clear benefits is like the integrated requirements in MBSE models, because before we did this, obviously our requirements and the system models that we built are totally not integrated. It's separate. It's very hard to um, see the assess the requirements coverage. For example, if you have 100 requirements, have you really designed your product to satisfy all the requirements? That kind of coverage assessment you couldn't do before because the data is not integrated. So that is a huge value add. And we also educated systems engineers about this MBSE methodology and tools, um, and instead versus the traditional systems engineering approach. And it's lower cost and high quality deliverables, because of course it reduces the time for the product development, and improved collaboration with the multidisciplinary teams, because it is easy for the downstream engineers to consume the data, rather than looking at the complex data. Siloed data with separate documents with no linkings, and now they can see from requirements to design to CAD, which improve the collaboration between those stakeholders. And we also used the MBSE Capella templates to reduce some errors and model iterations. So we have built some templates which they can use as baseline models to begin with, instead of starting the MBSE models from the scratch. This will reduce the learning curve, as well as the uh, shorter development time for building the models. And some of the learnings is like, in terms of IT implementation, we have to scope it better. If you're going with the MBSE implementation, especially with the integration of the PLM system, we have to consider our legacy PLM landscape. If it is a greenfield implementation for the newer companies, it's much more easier. But if it is a brownfield implementation like Applied, we have a legacy PLM landscape with a lot of customization. So we a lot of learning obstacles while implementing the solution, so we have to consider those things. And you also have to consider the data migration if you're looking into converting the existing documents into uh, team center requirements or MBSE models, how you are converting the existing presentation models into MBSE models. You have to consider those legacy data migration into your project scope. So some of our uh, future plans, that or projects that we are working on is key areas that we are working is MBSE adoption strategy, right? So yes, we have done this production pilot, a couple of product architectures. We have seen the huge value, but organization-wide adoption takes a lot of time, especially um, like the company like Applied Materials with a lot of multiple organizations with thousands of engineers. It is very hard to bring in that organizational change management. So how we can um, make it easier for the systems engineers not just to learn but also build the models. So what we are looking at is to leverage the GenAI LLM to automatically create the MBSE model elements in SMW or Capella using the requirements as an input, and also existing design documents coming from our applied materials internal design documents. So initially we will start with, okay, with the existing LLM. Okay, if you give the what is the LLM is going to give us the MBSE model suggestions based on the existing, trained model instead of using our own design documents or rack stack. That is our phase one. And phase two is use our internal documents and add the rack stack and use as an additional input for LLM to provide a better tailored response on what are all the potential, let's say, physical component nodes that are needed for this product based on the requirements and existing documents. So using that, and using py-capellambse or even Python for Capella mod add-ons, we could actually create the structure or different elements in Capella. So at least they don't have to start from the scratch. So in the Capella, in the left-hand side, you could see all the model elements automatically built. The baseline physical components and the structure is being built using our automatic. So that is something that we are currently working. We're soon we will hopefully in coming years we will share our learnings and accomplishments on that. And other aspect is like how we can programmatically create the architecture diagrams as well using Capella APIs. That is also one of our vision to achieve that in future. And some of the other focus areas is validating the modules and leveraging GenAI and Team Center to standardize the recommend syntax and formation and some of the derivation rules and restrictions for the recommend structure. So some of the other projects that we are planning in the upcoming years. And one other aspect I wanted to note down, just highlight, is like using the declarative modeling add-on and the py-capella MBSE. So since we build these complex models, we wanted to have a way of documenting these models in a very tailored fashion for a very niche engineers. For example, if the engineers, design engineers, are focusing on one particular subassembly, instead of going through the detailed, complex product architecture diagrams, we could create a diagram. We could create a simple document and where only that particular subassembly or particular physical component related diagrams will be automatically created in the documentation using declarative modeling add-on. So we have done some POC on this, so it is really promising. So we will create leverage that to create those individualized documentation for a very specific group. That's about it. I think if you have any questions, about our MBSE journey or how we leverage the MBSE to build the digital thread, yeah, I'm happy to answer, and I have Alondra here to answer. Unfortunately, Subhash couldn't join today.
Okay, thank you very much for this very interesting presentation, Nambu. The first question is about how it was received. Did the non-system engineering teams derive any benefit from the linked requirements and function or component information?
Yeah, so definitely because of the Tracelink, especially the design engineering group, what we are anticipating is, so for example, if you make a change in the requirements and make a change in the MBSE models and the design, so depending on the parameter change that you are making in the MBSE models, they could make a decision whether to revise the existing parts, or they want to create a new CAD design altogether. But again, we have done only the production pilot. In terms of real consumption from the design engineering group, we are anticipating a lot of benefits. Some of the real-time benefits, I cannot really speak. We don't have much data on that because we just started our production pilot stages.
Okay, understandable. Well, thank you for this answer. Then moving to the next question, still related to the tracelinks, how tedious was setting up the tracelink? Because it's a manual process, right?
Yeah, it's a good question. So again, as I mentioned before, it is multiple iterations, right? So when we develop the requirements, we also parallelly build the architecture diagrams in the MBSE in Capella. So it is a manual process, but it is part of your requirements decomposition process. It is part of your design process, right? So you don't see that as an additional process. So that way, engineers doesn't feel it as a tedious. But when it comes to creating a trace links with the CAD parts in the team center, since we have stopped at the level of sub-assemblies, So it's not huge, right? So you're not trace linking to like hundreds of components at least for now. So it is not that much tedious. But yeah, if you do that iteration process, for the recommend decomposition and design in parallel together in a collaborative manner, then yeah, it won't feel tedious, even though you're making those trace links manually.
Okay, interesting. Thank you. We have another question related to these requirements. So, have you experienced significant resistance to the adoption of MBSE and linking of requirements to MBSE artifacts?
Yeah. So yeah, I mean, definitely the especially bigger organizations, like we have tight timelines. So it's not, the resistance is not because BSE doesn't add value or anything like that, because our engineers already having a tight deadlines, because as you see in PPACT and other things, so the industry pressure is huge. So we have to bring our products to market quickly. So how to, without affecting the productivity, the product development timeline of our existing products, how we are bringing a new technology or new processes, with the learning curve, sharp learning curve. So it is very tough. So that is the reason why we are seeing resistance. It's not like the buy-in is not there. So almost all the senior leadership, engineering leadership, they are um, bought in this, and that's why we are doing this production pilot and doing a lot of things. One the resistance is only on that context, to answer your question. And the linking wise, the linking the recommends to MBSE artifacts, that we see a lot of pull from them. I mean, they really wanted it to happen. So there is no resistance for that, because that's a value they see, because that's a disconnect currently we have. They want to assess the recommends coverage for the design. And that is where the downstream lot of issues are happening. When they do the detailed design, they realize that, oh, okay, when they do the testing or simulation, they realize that, okay, it doesn't satisfy because you didn't consider these and requirements while designing it. So there is no really resistance on linking those artifacts. That's why we are focusing more on adoption strategy in upcoming years, like leveraging Gen AI to automatically create the models, even to the level of at least dreaming dreaming to create automatically diagrams in the MBSE. So that'll help tackle this resistance of adoption.
Okay, thank you very much. And finally, the last question for now is from Yondro once again. How do you or will you approach model creation and setup? I think Gen AI is quite a bit of an answer. Will you create a new Capella model for each project, program, product, subsystem, and so on? Or will you connect different models with one another?
So yeah, we started with some of the subsystems for our production pilot. Even our subsystems are complex enough, and the idea is to have all the product lines, and also have the configuration management for the products, right? So in the upcoming versions of SMW with Team Center. So SMW is like basically Capella will allow us to do the multiple configuration management. So for example, you could have one product, and you could have different variations of that product line. You could build the MBSE models in that. Um, so yes, so that is something we are planning to do for all the products, for example. And you talked about model creation and setup. For the manual one, we already have the SMW setup, which is Capella. We are currently using Capella 5.2, SMW 6.1, but we are planning to upgrade later this, in 2025. So where we will be using Capella 7. So manually, we can create MBSE models. And then once we created, we are already integrated the SMW with the Team Center, meaning once the models are created or matured enough, we will be releasing those models into Team Center. And since the Team Center integration is there, we could also drag and drop the requirements directly into the Capella so that the trace links can be easily made within the Capella itself. You could create trace links both in Team Center interface as well as Capella, depending on the configuration. So right now we have set up in a way that the requirements and the MBSE model trace link can be done within Capella, but the trace link between the MBSE models and CAD has to be done within Team Center. But in future we can extend that capability and bring it into the Capella itself. But in terms of automatic creation of models in Capella. So we are planning to use Python for Capella, GenAI to and even py-capella MBSE. So GenAI, we are getting the extracts in terms of a YAML patch format, and we use that to create the models in Capella. For example, to create the different elements in the operational capabilities. That we have already did some proof of concept on that. We are able to do that, but it's a matter of how good your LLM is at in suggesting, and also there are some limitations in py-capella MBSE YAML patches in physical architecture. So in system architecture and operational capabilities, we are able to create all the elements, but in physical architecture there are some limitations. So we are also exploring Python for Capella, how to run Python Capella outside of Capella application to facilitate that automatic creation of models in the future.
Let's go for a last
Sure.
one quick question. Since you mentioned limitations in py-capella MBSE, did you report those to the maintainers or consider contributing a PR?
Yeah, so I'm not 100% sure whether we actually technically created a PR, but we did engage with communication with the forums and the developers. So we have highlighted some of the limitations. But if there is a way to create a PR, then definitely, or some kind of enhancement recommend, we'll do that. Enhancement request, we will do that. But we have discussed those things, and we are closely following up the community forums to to get some answers and working on it. Yep.
Thank you very much again.
Thank
I will
you.
move
Thank
you
you, everyone.
off stage.